Hello, ladies and gentlemen. Uh, Good afternoon. So, welcome and thank you for attending uh, our episode here in One Quantum Philippines. So, today, uh, one of our members is going to present to you his experience in using IBM Quantum Experience platform. So, let me introduce our guest speaker. His name is Asher V. Manangan. So he is a member of One Quantum Philippines and is a fourth year student taking BS Computer Science at the Polytechnic University of the Philippines. So today he will give us a simple walkthrough on how to use the IBM Quantum Experience platform. So ladies and gentlemen, I give you Asher.
Hello, guys, and thank you, Sir Bobby, and to all everyone there on YouTube who are currently watching. So let me share my screen. So let me click present, share screen. Okay, then share. Okay, so great. So in today's session, we are going to discuss the IBM Quantum Experience, and here we are going to navigate and trying to work with its two main features. So, namely, we have the IBM Quantum Composer, as you can see in this screen, and we have the IBM Quantum Lab. Okay, and also we're going to perform some simple circuit runs and demo sessions as well. So, the IBM Quantum Experience is actually divided into two parts. Okay, so we have the IBM Quantum Composer and the IBM Quantum Lab. So, this IBM Quantum Composer is a web-based graphical interface that allows you to create quantum circuits right in your browser. Actually, you can drag and drop quantum gates and then create quantum circuits here, as well as it gives you visualizations such as the Q sphere, the probability outcomes. We have here the phase disks, also state vectors, and many more of its visualization features. So on the other hand, we have here the IBM Quantum Lab. So instead of dragging and dropping quantum gates to create quantum circuits, it allows you to run your programs using Python codes. So it makes you use of a Python library known as Qiskit. And also, this Python library, this Qiskit package, has a capability that will allow you to connect to a real quantum computer and run your quantum circuit. So in Quantum Lab, IBM will give you a workspace, and it's known as the Jupyter notebook. So next, so before we go into the demo of the IBM Quantum Experience, let's go first into a little bit of history of how IBM Quantum Experience have come into place. Okay. So 6 years ago, so it's 2016, IBM launches the first ever public quantum computing platform that is accessible for free to anyone. So the reason for that initiative is they have been into a constant request, right? They have been into a constant request from researchers and scientists. They are requesting the researchers from IBM to work and create a platform where they can validate and run their experiments on a real quantum computer. So we know that this request is not that just as easy to make, since it need to have a big backing from the community, because it will need to have a big amount of support, since they will going to put a lot of resources into the project. So the tipping point why I started to work with the project is where Isaac Chuang. So Isaac Chuang is the author of the book Quantum Computing and Quantum Information. So he asked on his conference his audiences if they would use a small scale cloud-based IBM quantum processor. So everyone raised their hands. So this convinced them to invest the resources building the platform. Quoting from Jerry Cho, so Jerry Cho is now the director of quantum hardware and system development. So he said that it gave us the validation that we had something and that we could get a lot of people behind it. So that's one of the reasons that influences them to work with quantum computing platform, this IBM Quantum Experience. So as you can see in this picture, okay, so this is a front end mock-up that they are trying to construct. So we know that developing a front end application was only one component of the problem, okay? So the team would need to consider the entire user experience, including how the users interact with the application, what features and gates they can see, and also how users can send their jobs to the backends. And also, one of the most important part is how to translate their created circuits into a quantum assembly language that a quantum computer can understand. So they've been able to work on these challenges and achieve a very good result. So by the numbers, so this data is as of May 2021. So we know that this is a little bit outdated, but uh, maybe the number today has doubled or tripled. But this is the latest data that we can find on the IBM website. So as you can see, we have 325,000 number of registered users in the IBM Quantum Experience platform. Also, we have 650,000 number of Qiskit downloads. We have 7,000 number of papers published using the IBM Quantum and 140 number of IBM Quantum Network organizations. Okay, so how does IBM picks a name for their quantum chip and backends? So they are in fact using the name of the birds as to represent the name of their quantum chips or their QPU, their quantum processing unit, and they're using the name of cities across the world where IBM has offices into, such as the IBM Q Manila, IBM Cube, IBM Washington, and the like. Okay. So IBM Quantum Experience also has different access plans. So here they have the open plan. So in open plan that is available right on the moment that you sign up on the Quantum Experience platform. So from there, you can have access to the quantum computers ranging from 5 qubits to 7 qubits as well. Also, they have the pay as you go model. Here, if you want to like work with longer run times, so for example, you're running your quantum circuit and it needs to run in a longer time that the open plan cannot accommodate, so you can work and subscribe with the pay as you go model. So currently, the pricing for the model is 1.60 USD per runtime per second. So it's all actually a very small amount to pay since most of the quantum circuits can run under a second. So even microseconds as well. Also, there is this premium plan model that you can avail as well. So the good thing about the premium plans model is you can have access to their latest quantum processing unit. For example, as of December 2022, you can work with their qubit processor, the Eagle processor. So it has 127 qubits. And also you can work with the Falcon processor, which has 27 qubits. And aside from that, they also have two programs that they're offering to educators and researchers. So we have here the research program. So it's intended for the members of the quantum information science community to get their research done faster. So the only requirement here is that the applicant must have at least one paper, preferably in the field of quantum information science, and of course that paper must be peer reviewed. So it's free of cost for academic institutions, and it's for non-commercial purposes. Also, they have the educators program. So this program helps teachers to provide the learning resources in their classroom-based settings. For example, they want to perform some demonstration, and of course, the demonstration must be achieved real time. So the advantage of the educators program is it gives you a priority mode. So it will reserve you time to jump your job execution onto the front. Also, this one provides a community, okay, a Slack community where you can collaborate with the fellow educators as well. So this is like a typical quantum computing platform architecture. So this is based on a paper called Quality Attributes on Quantum Computing Platforms. So as you can see, this is not directly on IBM's implementation of their quantum computing platform architecture, but this gives you a general idea of how does the quantum computer layers and the classical computer layers communicate. So for example, we have the business applications written in high-level programming languages. So these are the libraries we have. We have the Qiskit and Python. And of course, through these libraries, we can create quantum circuits, which we're gonna send to the quantum programming environment on the IBM's facilities. So these circuits that we've created will be transpiled into quantum states, quantum gates, and quantum devices. And this will be converted into a QASM language that the quantum computer can understand. And this will then be fed into a quantum computer and then give us back the result. Okay. And now for the demo, let's work now with the demo. So here are the things we are going to explore in the demo session. First, we are going to learn how to navigate inside the platform. Also, we are going to discuss about the quantum computing resources as well. And then we're going to work with the quantum composer and the quantum lab, and also create a simple demo application known as the quantum coin flip application. Okay, so let's go to our platform. So to go to the IBM Quantum Experience platform, just navigate here at quantum-computing.ibm.com. So here you will be greeted by your registered name. So welcome, Asher Manangan. So if you sign up with your name, you will also see it here. So it's really quite nice. And here in this section, you can see the notifications channel. Okay. So in this section, you can see the planned maintenance for the quantum computers. For example, here you can see that here are the quantum computers that will be into a maintenance on October 27th to November 7th. So this notification section will give you a uh, a course of action so that you can make some appropriate adjustments. So this notification section also gives you the information about the upcoming events as well. So this one, for example, is the IBM Quantum Challenge Fall 2022. So as you can see, this was announced here. So basically, this notification section will tell you all the things you need to know related to available quantum computers and current events. Also, in our dashboard, when you click this menu button and click the compute resources, okay, so this one is the compute resources dashboard. Here you can see all of the available systems on this your resources tab. Okay. So currently the highest qubits that I have an access to is 7 qubits, and the lowest one I have an access to is the 5 qubits. Okay, so you can actually upgrade to avail more of the qubits, and it depends on the access band that you have. Here on these all system backends, you can see all of the available quantum computers on all users, both for the free and premium subscribers. As you can see, we can access qubits up to 127 qubits, and the lowest qubit, which is 5 qubits. Okay, so here is the all simulator section. So you can also try to change the view by clicking on this section. If you want to view it as a table, you can click table. And if you wanted to view it as a card, you can just click card. So as you can see, here are our quantum simulators. We have 5,000 qubits, we have 100 qubits, we have 32 qubits as well. So one question that you might ask, why do we have 5,000 qubits here in our simulator, and on our real quantum computers, we only have up unto 127 qubits, and the recent one, which the Osprey, I believe it's 433 qubits. So the question is, why do we have 5,000 simulator qubit here? So what's the reason for that? So actually, this simulator stabilizer, as you can see, okay, does not simulate any circuit. Okay, let's wait for it to load. So this simulator stabilizer, although it has 5,000 qubits, it doesn't simulate any kinds of circuits. So, but it only simulates circuits that consist of specific gates known as the Clifford gates. So let me give you an example. So let's try to create a gates that's not belong to the Clifford simulator and run it onto the Clifford quantum simulator. So let's try to create a new file, and let's name it as Clifford Gate, Clifford Simulator. And then the Clifford circuits doesn't compose of 3 qubits. What if we add here 3 qubits gates? For example, the control not gate. So if I click setup and run, so let's add some measurement first. So if I click setup and run, and then let's run it onto the 5,000 qubit simulator, and click run. Okay, running the job as you can see here. Okay, let's wait for a meantime. Okay, let's refresh. Okay, as you can see, the job is failed. So when you click that and go into the more details, you can see that the transpilation turned into error. Since this qubit, this quantum simulator, although it has 5,000 qubits, it's only um, able to work with Clifford circuits. Okay, let's go back on our compute resources. So for example, we want to know more about the details of a specific quantum computer. So for example, here in the IBM Q Manila, so let's click IBM Q Manila. So when you click on a resource, you can see more details about it. For example, if it's online or if it's under maintenance as well. So here you can also see the total number of pending jobs, and also the processor type, the version, and things like that. And what is interesting here is the qubits. So take a look very carefully. IBM Q Manila has 5 qubits and a quantum volume of 32. Then if I go back and see IBM Q Lima, so it has 5 qubits, but it only has a quantum volume of 8. So what does it mean, right? So IBM Q Manila has 5 qubits, but a quantum volume of 32, and IBM Q Lima also have the same number of qubits, but have only a lower number of quantum volume. So what does it mean, right? So this quantum volume is actually a standard metric that is set by IBM. So the quantum volume actually measures the capabilities and error rates of a quantum computer. So the rule is the higher the quantum volume is, okay, the higher the quantum volume is, the more it is, the better and less error prone. So the lower the quantum volume, the more error it has. So let's take a look. So for example, this one. As you can see, the median CNAT error for this quantum computer for IBM Q Manila is 8.29 times 10 to the negative 3. And if we look the IBM Q Lima, the median CNAT error of the IBM Q Lima, you can see here, okay, let's wait. The median CNAT error is 1.28 times 10 to the negative 2. So as you can see, the error rates in IBM Q Lima for the CNAT, median CNAT error is much higher compared to IBM Q Manila. So it means that a higher quantum volume is, the more it is to be less error prone. Okay. So also, you can see here this CLOPS, which is the circuit layer operations per second. So this refers to the QPU speed of how fast you can repeatedly execute its circuit run. So the higher the number is, the better, since it will enable you to calculate much faster. And also, a very interesting thing here is this median T1 and median T2 time. So this median T1, this one, the median T1 time is concerned with the qubit lifetime. So this one will tell you how long can you tell the state one, okay? How long can you tell the one state from the zero state? So median T1 time is where time relaxation occurs. So currently, IBM Q Manila has a median T1 time of 186 microseconds. And the median T2 time, on the other hand, is concerned with the qubit phase coherence. So the median T2 time will tell you how long can be this quantum computer be able to hold coherent information before it can become unusable. Okay, so this is a more subtle aspect of qubits that is critical for accurate computation. This median T2 time is where the coherence occur. So as you can see, this quantum computer has a median T2 time of 47.37 microseconds. So basically, if the number is too short, the system can perform all of the necessary computations before the qubits lose their delicate quantum information. So here we have the map view. So as you can see here, we have this very interesting graphical representation. And this number 0, 1, 2, 3, 4 represents how many qubits does this quantum computer has. As you can see, it has 5 qubits. So when we look, for example, the IBM Oslo, so when we see the map here, we should see 1, 2, 3, 4, 5, 6, 7. So that's the meaning of the numbers of the circles there. And also, what I would like to show you are the error rates on each of the qubits. So as you can see, qubit 0 has a value of 2.47 times 10 to the negative 2. Qubit 1 has a value of 3.5 times 10 to the negative 2. Qubit 2 has a value of 3.5 times 10 to the negative 2. So why does it differ? Okay, so why does the qubits, even though they are on the same computer, same quantum computer, differ? So this is where the saying that not all of the qubits are created equal. So each of the qubits have specific properties. Some of them are less error, has lesser error rates. Some of them has higher error rates. So you can actually visualize this better on this graph view. As you can see, the readout assignment error for qubit number 2 is the highest. Yes, it's the highest, followed by qubit 1. And the least readout assignment error in this quantum computer is the qubit number 4. Okay, so also we have here the table view where you can see the T1, which is the qubit lifetime again. So this is where you can see the relaxation time. How long can you see the difference between the state 1 and to the state 0? Also, we have the T2 times, which is the decoherence time. How long can the qubit remain useful for computation? So you can see here the details of each of the qubits. Okay, great. So now we've discussed the quantum compute resources and hoping that maybe next year we can have access to more free qubits. But for us currently learning in quantum computing, this number of qubits are already enough. Okay. So if you want to like perform some really nice research, you may want to work with a higher number of qubits and see the differences. Okay, great. Now let's try to work with the quantum composer. This one. Okay. So as you can see, okay, the quantum composer. So again, the quantum composer is a platform where you can drag and drop quantum gates to be able to create your quantum circuits. So it's called composer because if you remember the composer from the music, all right, okay, from a musical note, you can see there that there are different notes that you can compose to create a beautiful music. So that's the same idea here in the IBM Quantum Composer. So instead of like working with uh, musical notes, what you can actually do is work with quantum gates, okay, to create beautiful quantum algorithms and circuits. Okay, so let's start with the basics. So as you can see here, the tool section where you can see the composer files that you've created. So you can load them up, you can share them. Also, this is the section where you can work with different gates, quantum gates. So you can work with this draw visual or this list mode. Okay. Also, here is the file menu where you can make a copy of your composer file that you've created. Also, you can share this quantum circuit that you've created. So the good thing about this IBM Quantum Composer is that when I share a circuit, for example, and I share it to the students, let's say this student doesn't have a prior IBM account. So if they just share this link, as you can see, the circuit that I have has been represented into their screens without logging directly into the IBM account. So they don't need to have an prior IBM account to see the quantum circuits that we have created. However, you cannot run the circuit without logging in. But that's one of the best thing about this one is you can share it anonymously as well. And also, we have here the edit menu where you can clear the circuits. For example, instead of deleting the circuits, these quantum gates one by one, what you can actually do is to just click the circuit, just click clear circuit to be able to clear all of the gates into the screen. Also here we have the theme. If you like to work with the different icons, you can just click this one, default all colored, default colored, the default is colored or monochrome. So me personally, I prefer colored. Okay. So right. So let's try to create our first quantum circuit. Okay. So let's say that we want to create a one quantum register and one classical register. So to do that, we can actually just click this one, the delete bit or this edit section here. So let's click manage registers. And then here, what we can actually do is to reduce the number of the quantum register to one, or rather, what's the better practice is actually create a new file. So let's name it as a demo one. Okay. So when you create a new file, by default, you will be given 4 qubits and four classical register and four quantum register. So that's by default when you create a new file. So for this first example, let's try to work with one quantum register and one classical register. Okay, so click OK. So what we can do is to click refresh, since we've discovered actually some bugs since this one doesn't refresh. So you can see it has still at 000. It should be like 0 and 1 only. Okay, so let's click refresh first to refresh our screen. So here you can see that we have one quantum register and we have one classical register. So let's try to create a simple measurement. Okay, so to measure our first qubit, so let's just apply this measurement and direct it to our first classical register. So as you can see, the probability outcome is 0. So what's the reason why it's 0? So by default, all of the qubits, okay, all of the qubits that we have is initialized into 0 state. So in IBM, working with IBM quantum computers, all of the qubits are initialized into 0 state. So if we measure it, we can actually arrive into a result of state 0, and it has a probability of 100%. Okay. So what if we apply an X gate here? Okay. So when we apply an X gate to our quantum, our qubit, our first qubit, you can see from the state 0 having a probability of 100%, it now transform into state 1, which have a probability of 100%. So as you can see, the X gate performs a rotation onto the outcome from state 0, okay, from state 0 to state 1. Okay, so also I would like to demonstrate the feature of the phase disk. So let's remove this first. Okay, so let's put the phase disk here. So if you want to work with phase disk, just click this one. So if I hover on the phase disk, you can see that the probability of being in state 1 is 0%. Okay. However, when I put an X gate before the phase disk, what will happen is that the phase disk now changes some information. So before, we have a probability of state 1 is only a 0%. Now, when we apply the X gate here, you can see the transformation, and now we have a probability of state 1 to be 100%. So how about if we apply a Hadamard gate, a superposition to this qubit, to our first qubit, and then let's work with the phase disk. So from a probability of state 1 to be 100%, now when we look at our phase disk, you can see that the probability of state 1 is now reduced to 50%. It's now 50%. Since we apply this gate, known as the Hadamard gate, which makes all of the possible outcomes for a specific qubit. So here we only have one qubit. So the possible outcomes here are 0 and 1. Okay. So very interesting things. Okay, now let's try to work with another example. And here, what we can actually do is to run our created quantum circuit here in the quantum composer. Okay, so let's name it as a measure. quantum measurement. Okay, real and simulated. So what I'm gonna actually do is to apply a Hadamard gate. Okay, so let's apply a Hadamard gate onto our first qubit. So as you can see, when we apply our Hadamard gate on the first qubit, we only have a two possible outcomes, which is 0 and 1. But if we apply another Hadamard gate into our second qubit, we have arrived into another probability outcome, which is 0, 1, 2, and 3. Okay, so the reason for that is if we only have one qubit, of course, the possible combinations will be uh, 2. So we have 0 and 1. So if we have two qubits, the possible combinations are 4. We have 0, 1, 2, 3, right? So if we add another Hadamard gate here, the possible combinations will now be 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what we can actually do is to try to run it on a real quantum computer and a quantum simulator and see if there is significant change in the probability outcomes. Okay. So let's try to measure our first qubit, our second qubit, our third qubit, and our fourth qubit. So to be able to run this on a real quantum computer, what you can do is to click setup and run, and then let's sort by the list BC uh, backend. So looks like we have a lot of total pending jobs here. Okay, so let's try to okay. So actually, I've tried to run this before, and for example, if we have a total pending jobs of 11, sometimes it takes 30 minutes or 20 minutes for us to see the results. So I have another account where I've actually run the this same circuit. So let's go there and let's go to my other account. So let me go back to my quantum lab. So we've actually done this because I am not sure if we're going to have a uh, available queue. So looks like we are sort of queue there. Okay. So let's go to our quantum composer. This one. So let's go to our composer jobs. Okay. Let's click this one. So when I click this one, so this circuit, as you can see here, okay, in the first presentation. So on the first account, so we have a 4 qubit register and we have 4 classical register. Okay. Then we have two Hadamard gates onto the first qubit and to the second qubit, and we have measurement on all of the qubits. So we've actually recreated this before in our second account in case we find trouble finding some access here since there's a lot of pending jobs actually. Okay, so as you can see, we ran this program a while ago, uh, last morning on the IBM QCASM simulator. And if I click see more details, okay, so you can see here is our circuit that we have on our first account. And when we do run it onto the quantum simulator, so we've run it into the IBM QCASM simulator, it gave us this probability outcomes. Okay, so we have 0, 1, 2, and 3. Okay, so out of all of the 16 possible outcomes, it gave us this 4 probability outcomes. So this is on the QASM simulator. And then I do run the same circuit onto the quantum computer, the real quantum computer. So I've run it on the IBM Quito. Okay, and as you can see, it has the same circuit. So look at the difference here, right? So it has the same circuit, however, it has more probability outcomes. So it has all of the 16. Okay, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, it has 15 possible outcomes compared to the IBM CASM simulator that only has four possible outcomes. So these are the four possible outcomes on the IBM CASM simulator. However, we also have these outcomes that where does this come from actually? Okay, so the reason that there's a difference between the IBM CASM simulator result and the real IBM quantum computer is because the real IBM computer has an actual noise. So the reason for this outcomes is because the quantum computers that we have today is prone to noise. That's why we have arrived with this results as well. Okay, and then okay, so that's very interesting thing. And also, one thing I wanted to point out is when we create our quantum circuit onto our quantum composer. So it's created via Qiskit. Okay, so it is not actually the real code. Okay, it's not actually the real code. Okay, this one, this code will is not the one that will be sent directly to the quantum computer, but the transpiled circuit, which is a custom circuit, which is you can see here. So this is actually the circuit that that's been transformed into a quantum assembly language, which will be fed into a quantum computer. Okay, so I hope that we've been able to work with the quantum composer. Like we've understand how to work with the gates, how to measure and understand the differences between simulating and putting it on a real quantum computer. And also, I would like to point this one out, the visualization seeds. So here you can have a visualization number from 0 to 99. So for example, this one, as you can see, let's see the state one. It has a probability outcome of 27.73%. However, if I do change the visualization seed, so let's say it's 8,000, okay, from 27%, now it goes down to 22.75%. So this is a cute way, a nice way to actually perform some randomness in the visualization, but it's not an actual visualization. So if you really want to know the measurement, you can run it onto the quantum computers on the simulator and the real quantum computer. Okay, so that's basically it for our quantum computer. I mean quantum composer, and we have discussed the compute resources. We've discussed the quantum composer. Now let's move on to our quantum lab. Okay, so this is on our fourth agenda for second to the last agenda, which is the quantum lab. Okay, so when you actually open the quantum lab, it will not give you a server right away, so you need to request for it. And IBM will provision you a Jupyter notebook workspace so that you can run and work with your code. So yeah, so here is the IBM Quantum Lab. As you can see, it's very familiar. It really looks like the Google Collaboratory. By the way, we have a video of Google Collaboratory by Sir Dylan Josh Lopez. You can actually see it in our YouTube channel for a very nice demo of how to use the platform. And then going back, so this will give you a workspace, this Jupyter Notebook workspace. And here you can see the files that we have. So you can actually create folders to separate your IPY NB notebooks or notebooks. Here you can have your files, you can download it, you can share it, you can edit this one, these cells here via this button. You can view here as well. For example, if I'm gonna present this one, I'm just gonna click this presentation mode. Okay. Also, if I wanted to run a specific cell, I can just click this one. So we can click this part or this part here that you can see as well. So if I wanted to restart or change the kernel, you can do this here. For example, if I want to change the kernel, we can just click this section. And also we have the tab section. We have the theme. For example, we can have the light theme. As you can see, it's the light theme that we have. But personally, I prefer the dark theme as well. And also the other customization that you can work is in this part. Okay. So a while ago, you've seen that we can create quantum circuits on a quantum composer, right? Actually, okay, our created circuits on a quantum composer visually can also be ported into code. So if you are a person who really wants to work with code, you can make use of the IBM Quantum Lab. So let's try to perform some simple exercises here. So in here, let's try to import modules from Qiskit that is required into this activity. So what you can actually do is to define our library, Qiskit, and then import the required modules. So quantum circuit is what we need in order to create a quantum circuit. IBMQ is what we need to actually communicate with the backend and run our quantum circuit on their quantum computers. Execute is a function where we can execute our jobs. Quantum register is where we can create our registers. Classical register is where we can create the classical registers. So this is uh, the libraries and modules you can actually use. So we also have here these two important part in this activity. So this job monitor will actually monitor the status of your submitted job. So instead of like going here on the job section in this part, so you can actually monitor your job status right in the terminal as well. So instead of going here, you can actually monitor it via this function, the job monitor. And of course, if you wanted to run it right away, your quantum circuit, you can work with the list busy function to try to filter out what's the least busy quantum computers. Okay. And then this one is a line of code which will load our IBM account. So the good thing about this quantum lab is if you're working on this quantum lab right away, inside this IBM Quantum Experience platform, you do not need to specify your API key. Okay, so the API key is found here on the account details, and here you can see here the API key. You don't need to actually specify that if you're working right here. But if you're working onto your personal Jupyter environment or in the Google Colab, if you want to work with IBM quantum computers, then you need to specify your API key there. So this is an added convenience. So let's click run. Okay. If you want to know if it's running or already done running, so if I click this one, this run here, you can see if it's on an asterisk, it means that the code that we've able to click run is still running. But if it returns a number, okay, it's the command is already done. Okay. So as you can see here, it gave us this one. Said that we've already run it. And then what we can actually do is to create a simple circuit with a quantum register of 1 qubit and the classical register of 1 bit. And let's try to add a Hadamard gate on the first qubit, then measure each qubit to the classical register. So what we can do now is to create a simple qubit with the register of 1 qubit. Then we create a classical register of 1 bit. And then we're going to create the quantum circuit. So to do that, we just specify any name of a variable equals to the quantum circuit. Then the parameters will be the quantum register and the classical register. And then we apply the Hadamard gate onto the first qubit. Okay. So to do that, we apply the Hadamard gate onto the index 0. So index 0 is our first qubit. So we do this one and then measure each qubit to the classical register. So if I click run, as you can see, the status is run. So it gave us this object. And then let's try to draw the quantum circuit. So to draw the quantum circuit, the syntax is the name of the circuit followed by dot draw and output equals to matplotlib. So let's click run. As you can see, we have arrived into this circuit. We have one quantum register, one classical register. We have the Hadamard gate on our first qubit, and then we perform some measurement. And the next part of the activity is we're going to get a list of the quantum backends and separate them as follows. So let's get a list of quantum simulators. Also, let's get the list BC quantum simulator. And then let's get the real quantum computers, list of the real quantum computers, and the list BC quantum computer. So optional, so you can use Preprint to have formatted results. So Preprint will actually make your returned result, returned list to be into readable format. So this line of code will going to give us all of the quantum simulators. So to do that, just type provider.backends, then followed by this argument. A simulator is equivalent to true. And then we get the list BC quantum simulator. So to do that, let's use this function list BC followed by these arguments, the backends and the simulator, which is true, and also with the quantum computers and the list BC quantum computer. So currently, before I've run this program, so the list BC quantum simulator is stabilizer and the IBM Keto. But if I run it again, so let's see. So here are the available quantum simulators for me. So the list BC quantum simulator is the IBM Custom simulator, and the least BC quantum computer we have is the IBM Cube LM. So before it's IBM Q Keto, now we have IBM Cube LM. So let's try to work with the IBM Cube LM. So to do that, let's try to create two backends. Okay, one for the simulator, and the second is for a quantum computer. So to do that, let's create a backend for our simulator and for our real quantum computer backend and click run. Oops, we forgot to replace it with IBM Cube LM since it's the least BC quantum computer we can use. So let's click run. Okay. And then let's run the circuit on both backends. So we can run this on a quantum simulator. Okay. So to perform the the execution of our circuit, what you can do is to use this execute function followed by these arguments, the quantum circuit, the back ends with the back end, the simulator back end, which is the IBM custom simulator, and the number of shots. So the number of shot is actually how many times you want to repeatedly run your quantum circuit. Because if you only have one shot, what could be the problem there is you might measure the wrong result. So you need to have a repeated number of measurement in order to distinguish the error, the probability outcomes, the real probability outcomes, uh, apart from the error that the quantum computers can create. Okay. Then here is the job. So this one will show the status of the job submitted and the result of the execution. So as you remember, we have this quantum circuit here. So the only possible outcomes will be 0 and 1. Since qubit 0 has two possible outcomes since it's on a superposition of 0 and 1. So to do that, let's click run the circuit. Okay. So the job is running. Okay. Okay. So as you can see on the IBM custom simulator, we have arrived into this result. on the probability of outcome having 0 is 524, and the probability outcome of being in state 1 is 500. So now it's queued. So let's see our jobs. Let's click refresh. So it's in a pending state. And sometimes this one is a little bit scary, since even though if you're on the queue of 6, you can see here that it can take up to 5 hours to run. So let's check our quantum computing resource to see if there's a way for us to actually filter out the least busy quantum backends. Looks like it's not. So let's click the jobs. Okay, this one will take a very very long time. So a good thing about this is I actually ran this a while ago. So it must have the same result that we have. So for example, if I run this program, so let's let it run in the background. So for example, this one will show the result in a very nice way. So you can just actually see it in this way, but you can also visualize it using plots, using graphs. So if I click run, so this will not run since there is a pending job here. So let's cancel the job. Okay, so we cancel it first since it may take a long time to actually achieve the result. So if I click run, since the simulator return a result, we must have a visualization. As you can see, we have the state 0 to have a higher chance of occurring, which is 524. So this is this one, and state 1 to occur, which is 500. Okay. And also, a while ago, I've simulated it on a real quantum computer and achieved on this result. So yeah, we're now able to see and work with the quantum lab. So if you prefer a quantum composer, that's nice. And but if you prefer quantum lab, that's also nice. So the good thing about quantum lab is it's very portable, so you can share it with your colleagues. They can run your quantum notebook as long as they have Jupyter notebook installed. Okay, so it could be on a Google Collaboratory here or on their local machines. So if you share the IBM Quantum Composer, the caveat there is they need to have an IBM account to be able to access your systems. I mean the to be able to access their editor. Okay, and here also, for example, okay, so for example, we have a scenario and we lose access to the internet, or we are somewhere try to vacation, and still we want to work with quantum computation. So the thing here there is you cannot work with the simulation if you don't have an internet, right? However, Qiskit, this very very nice Python library, offers you a way to simulate a quantum circuit on your local computer. So to do that, you can work with Qiskit Air. So Qiskit Air allows you to into perform simulations into your local machine. So for example, if you want to simulate 2-qubit systems, it's nice. You can simulate it in your local machine. But if you try to simulate your quantum circuit to have, for example, 100 qubits onto your laptop might crash. So this Qiskit Air is okay with small simulations for personal laptops that we have currently. So let me give you an example. So as you can see, if a while ago, if we want to work with the quantum simulators and the quantum computers, we provide here the provider and we load our IBM account. But here, so this is a program for working with Air. So as you can see here, we don't specify a provider. So we don't specify what quantum computer backend we wanted to work with. Okay, so this piece of code will allow you to perform quantum simulation. So let's create a quantum register of 1 qubit, classical register of 1 qubit, then create a quantum circuit, and then perform some measurement. And then before that, of course, we apply a Hadamard gate on our first qubit. Then it will print all of the available backends that we can use. And then we, of course, select the backend that we want to use. Then we execute the job by passing the quantum circuit that we've created, and then the backend that we've selected, and the number of shots, how many times you wanted to run your program. And then we get here the result, and then the counts, and it will print the number of counts. So if I click run, okay, so if I click run, as you can see, this line of code will give you the available backends. So here are the available backends on your local machine, and then you can actually select a backend. So in this case, we selected this backend, the custom simulator. So we specify here the custom simulator, and we execute the job and then print the result. So the counts. So as you can see, the counts has been printed, and the state one to being happening is higher than the state zero being happening. So that's a good way for you if you want to work with the quantum computing on your local machine. Okay, that's great. So now we've discussed three things. We've discussed the quantum computing resources. We understand their meaning, the backends, the details behind this quantum computer backends. We have the quantum composer. We have the quantum lab. Now we work with our demo application that we have here. So this is our last agenda, which is showing you how to implement this simple demo into a real project. So it's a very simple project. So this project is known as the Quantum Coin Flip app. Okay. So this Quantum Coin Flip app. So actually, the idea behind here is we're gonna work with a real quantum computer to flip the coin. So what does it mean to flip a coin? So if we get a result of for example, we have one, we represent this as heads, and we have zero, we represent this as tails. So if we have the highest number of probability outcome occurring, that will be the result of our coin flipping. Okay. So this application is actually on GitHub. So if you want to work with GitHub, I mean, in this project, you can actually copy this code, this URL, and go there. And here you can see the code, and it's open source. Feel free to contribute. And this one is made using Unity as the front end, since it allows us to easy prototyping. You can drag and drop user interfaces compared to JavaScript, where you still need to know where is the location of the div. So Unity is a really recommended way for us to prototype fast. And also, we have here Django as our backend. So this allows us to communicate directly into the quantum computing platform from IBM. Okay, I'll post the GitHub URL here. So I'll show to you again this one. So maybe you can screenshot this one. I will comment this later. Thanks, Ahmed Zahir. Okay. Okay. So what you can do is just to clone this project, and then after you've cloned this project, you can then open Unity. So make sure that you have Unity installed, and if you have Unity installed here, you can see here the application that we have. So before we are able to make this work, of course, we need to run our backend, so our Django application. So let's click this one, Quantum Coin Flipper. Okay, so to run this one, make sure that we are onto the correct directory. So let's go to our backend. Okay, backend. Okay, then to be able to run this backend, so let's just type Python. So it could be Python, it could be Py. So in my system, it wants to use Py. I don't know why. So Py manage.py, then run server. So when you perform this command, it should give you this result. Now it's listening on port 8000, and it's now ready to accept request. So let's go here, and then let's click run. Okay. So I hope that you are hearing some very cute sound here. So you can actually work with this one. So it has animation, and to get started, let's click this red button. So we need to input our IBM API key. So let's get our API key here. So let's click copy. Okay, and then let's paste it here. So as a disclaimer, this program is still not secure, so this is only for demonstration purposes. So if you really want to try it on your own, it's recommended to change or regenerate your token after you work with this app. But feel free to offer some possible solutions how we can make this a better one. Okay, so after we've inputted our API, we just click next, and then here we can get the list of all of the backends available on our subscription. So let's just wait. So as you can see, when I click list all backends, it now acknowledge it and then post that, and let's wait for the result. So as you can see, it gave us this result. These are the available backends available to us. Okay, then if I click next, here we're going to choose the backend that we want to run our quantum coin flipping. So let's try to get the list busy backend to get, and let's see if we can actually work on that real quantum computer as long as it is not busy. So it's now loading, and let's wait for it to load. So it's now waiting for the results here. Okay, let's wait for the meantime. Okay, as you can see, we have IBM Cube LM as the list busy backend. So let's just check first if it's really not that busy. So let's go to our compute resources, and then to our total pending jobs, and see the IBM Cube LM. Yeah, so it has like 14 pending jobs. So let's just use for this one. Let's just use a simulator. So let's just use this one, the IBM Q custom simulator instead. So you just type it here, then click next, then click flip. So let's just wait. Okay, as you can see, it gave us a result, which is heads. So we assume that the value of state 1 is higher than the value of state 0. So the job ID is this one, 8C0. So we can actually verify that here by clicking jobs. And then you can see here that we've executed it on the IBM Q custom simulator. And here is the job, the 8C0. As you can see, state 1 occurs higher. It has more counts, 521 compared to state 0, which is only 503. Okay. So yeah, you can use this one to tell and share it with your friends, and feel free to modify the code. So it's open source, and I will just to explain a little bit of the code. How do we make this happen? So the most important part here is this results API. So when we click the flip button, right? So when we click this flip button, it will then call this API URL, this slash results, and then it will get the API key, okay? And then it will get the backend that we have provided. So we provided the IBM Q Custom Simulator, and then we then specify the provider, which is on our current subscription. We have our hub as an IBM Q, and then we select the backend, and this is the part where we construct the coin flipper. So we this circuit is actually very simple. So if you remember our quantum lab, right? So this circuit is the circuit that we've also implemented here in our code. So we just apply a simple Hadamard gate here and then measure. Okay. Then we execute this onto the quantum computer by passing the circuit, the backend, the IBM custom simulator, and the shots. And then the job has been monitored and print the results. So this line of code here, as you can see, this result will tell you if the it will going to give you, it will assign a number of the most frequent count. So the result will return a most frequent count if it's either 0 or a 1. So if the most frequent count is 0, then it will going to return tails. And if the most frequent count is 1, then it will return heads. So after that, we close the account and then return the response to be visualized back into our quantum computing front end. Into our Unity front end. Yeah. So feel free to work on this one. And basically, that concludes the presentation. And thank you very much.